Hey, Dia here. And would you look at the time? It's episode 12. Oh, how time flies. So, this episode marks the last example episode of the Pseudo-Focus series, where I will showcase to you other interesting functions and their pseudofoci. And good news, no algebra. I have done that dirty work for you, finding the PFs myself, because I had a change in heart. That I want to emphasize more on the stunning visual aspects of the normal maps and the cone graphs themselves, of which I will showcase this video. The thing is, we just get so focused on the algebra that we forget what we were trying to solve, shifting our focus away from the significant and contextual images, like how close normal lines forms a normal map, like how all the intersections in a normal map draw the cuspy cone graphs, and like how the cuspy cone graphs are actually the x and y components, or subunion 4, used as a parameter. Hence, I will reconsider what makes my videos entertaining by focusing, no pun intended, focusing more on the good, wow-inducing moments behind the math. So the first example we'll look at is secant x. Let's investigate. Secant x is simply cosine x's reciprocal, which means if cosine x is 1/2, secant x is 2. If cosine x is 1/4, secant x is 4. But if cosine x is 0, secant x is undefined. Since cosine x regularly hits the 0 mark, like infinite times, secant x regularly hits the undefined mark infinite times. Now, how about their pseudo-foci? Well, to start, a single mound has an upright curve, so the approximate method can be used here. Doing the easy work for you, this mound's PF comes out as 0,2. Subsequently, we have the second mound, where this is simply pi -2. Since secant repeats like sine and cosine, we assume the same pattern of PFs to every repetition of 2 pi. Therefore, our infinite PFs are expressed as 0 plus 2 pi n2 and pi plus 2 pi n -2, where n is an integer. Okay, secant has simple PFs. Isn't that unchallenging? Or is it? You have every right to doubt this fact, but there are actually 3 pseudofoci in one mound. If you look at the normal map, it will seem like there is one corner, but when you zoom in, there are 3! 3. You still can't see it. Look at the cone graph. 3 corners. However, this isn't the real big deal about this function because the sinister part of it is the algebra. Now I said I didn't want to bring up the algebra, but look at the step 2 equation. It's horrifying. Look at my attempt of solving it. I just give up with my head down in distress because I have no choice but to use an algebra calculator. And when I saw the computed solutions, I was half glad to have given up because the solutions were so monstrous that I wouldn't have found anyways. Looking here, this first solution is for the simple PF that we got. But 2 of these are other solutions in the first mound, while another 2 for the second mound. Now imagine step 3 and 4 and plugging these 4 other solutions out. 4, I say. But fortunately, we have Desmos to point out the other PFs with ease, where those are on 0.026 plus 2 pi n, 1.901, negative 0.026 plus 2 pi n, 1.901, 3.115 plus 2 pi n, negative 1.901, and 3.168 plus 2 pi n, negative 1.901, where n is an integer. What turned out as an innocent and simple trigonomic function is actually a mathematical death wish when you try to find its pseudofoci. Let us try something much simpler, an ellipse. For our purposes, we need to express the oval to a function, or perhaps 2, where we have f of x equals plus minus 2 times the square root of 1 minus x squared. For a start, the real focus of this conic is 0 plus minus root 3. And for comparison, the pseudofocus is different for the ellipse, where we find them on 0 plus minus 3 halves. Now, here's the cool part. The normal map, where we see this star. First of all, this star shape here is what is called an asteroid, and it has these 4 edges. 2 of them touch the pseudo-foci, and the other 2 are... Wait, then that means we have 4 pseudo-foci. So it's also -3,0 and 3,0, which is outside the oval. Basically, the pseudo-foci of the ellipse are the points of the star-shaped asteroid. Tell you what if we could find the pseudo-foci of an asteroid? Surprise, surprise, we can! A function graph of an asteroid is f of x equals plus minus 1 minus x to the 2/3 power to the power of 3/2. Now, let me spit it out. The pf's of this star are root 2, root 2, negative root 2, root 2, negative root 2, negative root 2, root 2, negative root 2. Oops, all root 2. But look at this. We get 4 pseudo-foci from an asteroid, which is interesting because what then would the normal map look like? A square? Close, but the normal map shape is actually another asteroid, but bigger. Specifically, 2 times bigger, because it encloses the original asteroid perfectly in a diagonal fashion like that of squares. Now, if the cone graph of an asteroid is an asteroid, then that means the normal map of this next asteroid should theoretically be another asteroid. Unfortunately, we cannot graph this second asteroid as a function, but we can imagine another asteroid 2 times as big and rotated another 45 degrees. In that sense, we just thought of an asteroid 4 times as big as our first one. Overall, this only works for the square-ish asteroids, unlike the stretched asteroid from the ellipse, of which I will leave you to find out. Let's transition to a curve similar to asteroids. Y equals x to 2/3 power. Now, this curve is similar because it looks like a cone graph, which it is. More specifically, it's the cone graph shape of x squared. This is interesting because what would the cone graph of this cone graph look like? And where could the pseudo-focus be? Think about it. For a start, let's see when we draw every normal line of this curve. So here you go. First of all, look at this. The normal map just leaves out this parabolic hole. It's as if you shone UV light to bacteria on a petri dish. It's so satisfying. Since the parabola is a recognizable shape here, then the quote-unquote cone graph is just a parabola. Now the question is, where would the pseudo-focus be? Well, the PF is considered to be on the tip of the parameter, so it should be 0, 0. However, there's a big but statement here. It should be 0, 0, but 0, 0 does not exist in the parabola's domain. Why is this the case? This is because the normal map does not clearly draw the full parabola close to the origin, no matter how dense you make it, because how do you even draw 2 different lines at a point? You can't. Even if infinitesimally dense, it is still a bigger gap than a singularity of 0. And lastly, the step 3 and 4 values give you an undefined value. Well, okay, so what is the pseudo-focus then? The answer is no. No PF. Sorry, it doesn't exist. Pseudo-foci are those points that are just there by nature in every curve, in every graph, with a few exceptions, of course. Our pursuit of finding this point has led us to some amazing wonders about cool line art and cool shapes, essentially giving these curves so much mathematical meaning that I can't stop pogging about it. I'm sorry. But we are only scratching the surface of what curves we can find the PF, the normal map, and the cone graph of. Curves that, may or may not be drawn and expressed from the behavior between x and y, but expressed from the separate behaviors of x and y individually. See you next video.